Assalamualaikum warahmatullahi wabarakatuh. Welcome back to my video. So now let's continue with chapter number 3 with the title of Induction Motors. And we're gonna see some of the outlines or some of the outcomes at the end of this topic. So whereby student will be able to know the fundamental. Okay, so this is the fundamental of induction motor. The constructions, of course, as well as its basic concepts. And then number 2, so you are able to understand the equivalent circuit of an induction motor. So we have seen in previous chapter how we convert or how we actually transformer into its equivalent circuit. And this time around, so we're gonna have the same process whereby the equivalent circuit of the induction motor will be later introduced. And third, to analyze the power and torque plus the torque speed characteristics. Okay, and then fourth, you must be able to recognize method on how to start, and then the method on how to control the speed of induction motor. Then number 5, so you must be able to determine the circuit model parameters, particularly for induction motor. And last but not least, so you should be familiar with the induction motor rating, especially the data available on the nameplate of the induction motor. Alright, now we jump over to the next slides, which emphasize on the induction motor construction. And you can clearly see over here the picture of the cross-sectional picture, for example, of the induction motor that consists of a stator, right, the one which is static, and then the moving part, or the rotate part is actually the rotor. Okay. So the drive end, so this is the extruded shaft over here. Okay. So this is the non-end drive. Okay, so the hidden shaft inside the machine or inside the motor. The fan, all right. So the purpose of the fan is for cooling, and the air flow over here, as well as the fin shape of the outlook or the outside design. So this fin is actually for air flow cooling. And then the single phase induction motor is the most frequently used motor in the world. Okay, and then the most appliances, for example, home appliances, you can see washing machines, the refrigerator, so use a single phase induction machine. So this is the reason why induction machine is one of the most used machine worldwide, and some of the reason again due to his robustness or the high reliability of the design, as well as the low cost. Right? So it is called an induction machine because the rotor voltage is induced. Okay, this is the keyword, in the rotor winding instead of physically connected by wire. So this rotor voltage is actually producing a rotor current, also rotor magnetic field. So since there is no DC field current, and it is which required to run the motor, okay, then mostly used as motor instead of generator. And basically there are two types of rotor, so namely the squirrel cage and the wound rotors. However, most of the design of the motor design use squirrel cage, because of the robustness and also the maintenance-free construction. So here we go. This is how the squirrel cage rotor looks like. So basically we have the shaft again over here. All right. So the other end or the other side of the rotor, we have another shaft, and then we have the fan blades over here. Okay. So attached to the aluminum ring. All right. And then in between these two aluminum ring for this, for example, this side and this side. All right. So we have the aluminum bar, the one with this silver color. All right. So all these are aluminum bar, and in between this aluminum bar, the brownish color, dark brownish color over here. All right. This one, this one. They are all actually laminated iron core. And you can see it is okay. It is designed in a form that the aluminum bar is a little bit skewed or slanted. Okay, it's not a straight connection between two aluminum rings. Instead, we have skewed in certain angle. So the one I color in yellow, for example, here. All right, so a bit skewed, a bit slanted for certain type of reason, which we will discuss later on. And here some of the description on the squirrel cage rotor and some of the illustration. So we have the end rings, both sides, side number 1, side number 2. So we have the rotor bar, which is slightly skewed. And again, this is in the animation, the 3D animation of the squirrel cage rotor. So this rotor has a limited iron core with slots and is mounted on a shaft. Okay, this is the basic construction of the rotor. And then besides, we have aluminum bars which are molded in the slots, and bars are short circuit between two end rings. So all this one, the brown color over here, so it's an aluminum bar which is slot molded in slot and connected with two ends of rings. So the bars are slanted on a small rotor to reduce audible noise. So this is the main reason why we have the skewed or the slanted form or configuration of the aluminum bar. So it is used to reduce the audible noise. So fins are placed on the ring that shorts the bars. So the fins work as a fan and improve cooling. So this is the fan, the blade, you can see. Okay, comes with the fins, and it works to improvise the cooling effect. So on the other hand, we have the wound rotor. Right? So wound rotor, this is actually similar to stator windings, or especially the three-phase winding, where such behavior of wound rotor machines can be controlled by adding resistance to the rotor circuit, as shown below here. So this is the schematic. So we have the V line to line as the phase. Supply, for example, and then we have this connected in Y configuration, okay, between line 1 and 2 and line 3, or RYB, red, yellow, blue. So in terms of income circuit or the equivalent circuit over here, so we will see later on in more details, so how we actually come up with this equivalent circuit. However, to share with you in this particular slide, so we do have this additional R that installed in this one rotor. And in terms of construction, we have the slip ring part over here. The component, okay, is actually to allow the current to flow. So, and in all, so the price is quite high compared to squirrel cage. So one rotor induction machine have a three-phase winding similar to the stator winding on the rotor. This is what I have explained earlier. So the rotor is usually Y connected with terminals of the three-phase connected to slip rings. Again, this is have highlighted before. So in normal operation, the winding and the slip rings are short circuit to allow current to flow. This is the basic uh, function of the slip rings, where it allows current to flow. And then an advantage of one rotor machine is that external circuits can be connected to the rotor, that allowing external control of the machine. And besides, one rotor induction machines are usually significantly more expensive than squirrel cage rotor machines. So this is to wrap up why the this type of rotor is difficult to be found in market. So possible applications for one rotor machines include the speed control of very large machine up to multi-megawatt. Okay, and then to reduce cost control of large machines, and particularly in W-fed induction generation, where it is utilized in some of wind turbines, whereby DFIG or W-fed induction generation is actually consists of two active winding set, namely a stationary part as well as the rotating part. Now the development of induced torque. So just imagine we have our stator over here, all right. So with the winding, so this is the okay coming out of the into the page or into the slide. Over here, the winding is going out of the page or going out of the coming out of the slide. And then first steps, we apply the three-phase voltage to a stator, of course, here through this winding or this coil. So apply three-phase voltage and then three-phase current flowing in stator that produce BS. All right, so this is the illustration of BS. So what is BS? So this is a maximum induced voltage, whereby BS is a magnetic field, which is induced voltage in rotor bars, and it is actually rotating in counterclockwise direction or CC direction that cause rotor to accelerate. Okay. And then yes, the maximum induced voltage from the induced magnetic field, and here we are able to come out with this relationship where the n syn or the synchronous speed equal to 100 multiplied by Fe. Fe is system frequency, the electrical system frequency, as the P is this number of pole of the motor. Okay, and then yes, we have the W as well, the angular velocity. And now what happened next is IR will be induced. So this is nothing but maximum induced current. So this induced current is again induced by maximum induced voltage over here. All right, and jump over to maximum induced current. So again from here BS, so we'll induce maximum voltage in rotor bars again, I repeat, and then rotor voltage produced here from rotor voltage produce a rotor current flow or maximum induced current over here IR, and then from IR here produce rotor magnetic field BR. Right, so this is the sequence how all the maximum voltage induced current, for example, and also the rotor magnetic fields are being induced. So next is the B net. All right, so the magnetic field, the net of magnetic field after we produce or we induce stator magnetic field as well as the rotor magnetic field. So we have the B net, and yes, again we'll induce ER, which is the net voltage. Okay. And how to calculate the induced voltage? So E induced equal to V times B dot L. So the magnitude of V times V again times L. Alright, so theta R, again, this is between B net or ER and the phase shape between ER and IR. So back to E induced or induced voltage over here, V times B dot L, where V is actually, if you can recall in chapter number 1, so we have cover this equation whereby V again is the velocity of magnetic field, right? Sorry, and then B is density of magnetic field, and L is the length of conductor in magnetic field. Now, since BR and BS have been induced and rotate at n-sync, the synchronous speed, so but rotor turns at a slower speed. So this is what happened to the rotor. So they tend or they try to catch up the n-sync. Okay, so the n-sync or the synchronous speed is actually the direction between BR and BS, or produced by the direction between BR and BS. And due to that, rotor is now rotating or turning at slower speed and try to catch up the n sync, the synchronous speed. So back to the induced voltage E induced over here. This is actually the voltage induced by BS, right? The stator magnetic field. Okay, so since we have produced BR and BS, so now the machine is able to induce the torque, okay, or the induced torque. Some of the qualitative descriptions, the three-phase stator winding is connected to a three-phase supply. However, this is what I have explained in previous slide, and we try to come up with this description in more details. So current flow in the stator winding producing a rotating magnetomotive force and flux density. So this is the reaction after we have the three-phase supply as well as the current supply to the stator winding, and then what happened to the stator flux. So it rotates at synchronous speed. So this is the relationship, and S equal to 120 times Fe over P, number of pole for and the unit is in RPM, radian per revolution per minute. However, if you want to convert to radian per second, so we have radian per second. We have this equation omega S equal to 4 pi Fe over P. So the magnetic field passes conductor on the rotor and induce a voltage in those conductors. And then, since the conductors are short circuit, current flow in the rotor conductor. So now current start to flow inside the rotor conductors, and then this current produce a second rotor magnetic field which acts to oppose the stator magnetic field and also rotate at synchronous speed. So this is known as the BR, right? So this is known as BR, which rotate at a synchronous speed. So with two magnetic field rotating at constant speed, BR and also BS, a torque is induced with K1 constant. So then the rotor flux density, again, this is BR, will lag the stator flux density. This is BS, okay, which is lagging current by 90 degree electrically. So therefore, the torque will be in the same direction as the rotation of the magnetic field. Right? So the torque then accelerates the rotor until synchronous speed is reached. So at which time there is no relative motion. So when there is no any relative motion between the two conductors and also the flux density, the stator flux density. So since the relative velocity is zero here, so no relative motion, so the induced voltage, the rotor currents, the flux density fall also to zero, and torque is zero as well. Okay, so to say that when to no different in velocity, especially at synchronous speed, So we can say that the induced voltage and then equal to IR equal to BR. Okay, this is equal to 0, and thus torque equal to 0. Okay, now so we move on to the concept of rotor slip. So what does it mean by rotor slip? So the voltage induced in rotor bar depends on the speed of the rotor relative to the magnetic fields. Okay? And having said that, to two terms to define the relative motion. So first we have the slip speed, and second we have slip. Okay. So now back to slip. What is definition? It's nothing actually but a difference between synchronous speed and rotor speed. So we have n slip over here, which is equal to synchronous speed minus nm. So n slip is slip between, slip speed of machine here. Again, I repeat, this is slip speed of machine, and n syn or synchronous speed is speed of magnetic field. What about Nm? So Nm is mechanical shaft speed of motor. Okay, so hope you can get it. So what about how about slip? So relative speed expressed on PU basis as shown down here. So S equal to N slip over N syn. Okay. Or we can write in terms of omega, whereby S equal to omega syn, synchronous omega, minus M syn speed omega over omega syn. Okay, so we try to derive the equation and to come up with this final relationship where Nm equal to 1 minus S and syn. Okay, so let's take from here. So we have S over N slip. Okay, sorry, S equal to N slip over N syn. So what is N slip? N slip is here. Okay, the one in yellow box. So we have N syn. Okay, N syn minus Nm over N syn. So now we need to rearrange the equation. Okay, this equation into here. Nm equal to negative S and syn, right, plus and syn. Okay, and then finally from here factorize. Here we got 1 minus S and syn. Similar equation with this one. Okay. So from the previous equation, notice that if the rotor turns at synchronous speed, S equal to 0. Okay, so rotor turns or rotor rotates at synchronous speed, S equal to 0. While if the rotor in stationary, S equal to 1. So how to prove? So since we and then before that, all motor speed fall somewhere between those limits. Okay, this means the motor speed fall somewhere between S equal to 0 up to S equal to 1 as the maximum. So now get back to our equation where Nm equal to I minus S, not I, but 1 minus S and syn. Alright, and syn. So let's say S equal to 0. So S equal to 0, that means slip is 0. So we know that Nm is now equal to Nc. Okay. So this is what it means by this statement. Rotor turns at synchronous speed. Okay, because Nm in this current condition equal to synchronous speed. So what about if S equal to 1? So equal to 1, that means there is no speed because Nm equal to 1 minus 1 is 0. Okay, that means the motor is in standstill. It doesn't rotate at all. Okay, speed is 0. So meanwhile, if s equal to 0, so Nm will reach its maximum speed or its synchronous speed and sync. Okay. So this is the reason why the motor speed must be fall in between s equal to 0 up to s equal to 1. Okay. So the electrical frequency on the rotor. So induction motor, also called as rotating transformer, due to its induced voltage and current. So primary or stator induce a voltage to secondary or rotor. So unlike transformer, so this is actually the comparison. Sorry, back to this paragraph or this point. So primary is referring to stator of the motor. Primary of what? Primary of transformer. Okay. So referring to stator. And secondary, while secondary is referring to rotor of the motor. Okay. Secondary of transformer is referring to rotor of motor. And then unlike transformer, frequency not necessarily same as at secondary and primary. So if rotor is locked, so Fr equal to Fs. So the rotor frequency equal to the stator frequency, or Fe. Right? So the system frequency, whereby S equal to 1. Because according to this relationship, we have Fr, the rotor frequency, equal to S slip Fe. Okay, the system frequency. So if rotor is locked mean motor doesn't move, S equal to 1. Okay, so F equal to 1. So substitute in this equation. Now we have Fr equal to Fe, or F equal to Fs. Okay. So about if S equal to 0, now again into this equation, so Fr is now equal to 0. Okay, so rotor at and synchronous speed. So for any speed between the rotor frequency is directly proportional to the difference between the speed of the magnetic field and synchronous speed, and the speed of the rotor and m. So again, this is the equation S equal to nc minus n over n sin. So now we have this equation or relationship where Fr equal to SFE, and finally we are able to come out with this final relationship where Fr equal to P over 120 NC in bracket NC minus S and M. So how to derive? So let's say we start with Fr equal to SFE, right? So this is equation number 1. So next we have Fr equal to what? So this is equation number 2. Alright. So now 2 into 1. Okay, 2 into 1 means this S is now replaced by n sin minus n m over n sin. Don't forget all these times F. Okay. So now this equation is taking part. Alright, so we have Fr over here. So let's say this is the third equation. So now the third equation into here. Alright. So now we have Fr, okay, is finally equal to P over 120 in bracket and sin minus n m. We can simply write that this is actually Fr, the rotor frequency, is actually P over 120 times n slip, because n slip equal to nc minus nm. Okay. Alright, so now example number 1. So a 220 volt 3-phase 6 poles. So this is the P, number of poles, 6 poles, 50 Hertz induction motor is running at the slip S of 3%. So S equal to 0.035 or 3.5%. Right? So find the speed of magnetic field in RPM. So this is the unit. So you need to calculate the speed of the magnetic field in RPM. So speed of the rotor again in RPM. So the slip speed of the rotor, and as well as the rotor frequency. Okay, so let's look at the solution. So solution number 1, the speed of the magnetic field is, here use this equation, n sync equal to 120 Fe over P. Fe, the one is provided in question, 50 Hertz times 120 over 6 is number of pole. Okay, this is also provided in question. Okay, so solving this, we can calculate the RPM speed of the magnetic field, which is 1000 RPM. So B, the speed of the rotor is, so Nm equal to 1 minus S n sin. So use this equation. So and then substitute the value of S, which is 3.5% or 0.035. So multiply by the n sin, so the value we just calculate above. Okay. And the speed of the rotor is now 965 revolution per minute. And you can see that apparently the value of speed of rotor is slightly slower or lower than the synchronous speed over here. Okay, this is 1000 and this is 965, because this is the magnetic field speed, or the speed of the magnetic field. We can say that this is actually theoretically the speed, the ability of the maximum speed the motor can have or can run. But when it comes to the speed of the rotor, the actual, so due to some of the issue, for example, the slips, okay, due to the slips, the 3.5 slips, that cause the motor slightly slower compared to the magnetic field speed or the synchronous speed, which run at 965 revolution per minute. So what about the slip speed? So it's simple, it's the difference between the magnetic field speed or the synchronous speed here, and also the rotor speed. Or we can write in this, or we can solve using this equation. N slip equal to slip or S and sync. So 0.0035 multiplied by 1000 RPM, so giving us the slip speed is 35 revolution per minute. So the rotor frequency, so Fr equal to N slip P over 120. Okay, so this is what I have shown or I have derived earlier in order to come out with this relationship. So just substitute the value of N slip over here from this 35 RPM into here and multiply by 6 the number of poles and divided by 120. So giving the rotor frequency is 1.75 Hertz. Okay, that's all from me. So I hope to see you again in my next video. Have a nice day.